All right, welcome to the Friday Transportation Seminar at Portland State University. My name is Chris Monsieur. I'm in the Department of Civil and Environmental Engineering, and together with my colleague, Dr. Wang, we co-organized this seminar along with many of our other faculty in the transportation area. Today we're very pleased to have Dr. Sal Hernandez. He's newly arrived in Oregon. He's at Oregon State University for a few months now, so he's presenting today on a topic that he did where at his former place where he's at the University of Texas at El Paso. So we're very pleased to have Sal today to give us our talk. And for students, I forgot to bring the registration form, so I'll do that electronically. But when you ask a question, make sure to announce your name. So with that, I'll turn it over to Sal. Welcome.
Thank you very much, Dr. Monsieur and Dr. Wang for the invitation. And just to let you know, I do speak Spanish. If you feel more comfortable asking me questions in Spanish, that's okay. No one knows what you're actually asking. That's even better, right? You can ask me something. So just to kind of reiterate what Dr. Monsieur said, I just arrived in July. I just started doing some research here in Oregon. I'm actually a West Coast guy. I was born and raised in Southern California. Well, so I should say West Coast. So that's something that I had to get used to. We have beaches in California. You have coasts in Oregon, right? So that's the thing that I had to a beach with sand, right? So that's the thing that I had to get used to. So I was 15 minutes from the beach, so I used to get a little sun there. Now I'm about 40 minutes from the coast. So just a little bit of background before I begin. I graduated from Purdue University with my doctorate degree. I did it both in econometrics and network modeling. So I was co-advised by two professors from Purdue in that area. So my research topic is, well, at least the topic for today's seminar is one of the last studies that I performed at Texas in El Paso with one of my former PhD students, Muid Islam. I want to make sure I give him credit. This was part of his dissertation work. He is now at CH2M Hill and the safety office in Chicago. So he's out there doing his work and continuing some of his research. My topic is modeling injury outcome crashes involving heavy vehicles on Texas highways. So see if I get this to work. So to kind of give you a little bit of background on why this topic, why we were interested in this topic, just from a regional perspective, we were in El Paso. So the El Paso sister city is Juarez, which is connected between a port. We were just divided by a port of entry and a small little river called El Rio Grande. I hardly had any water, but they call it El Rio Grande. And so, El Rio Grande, right? And so there was a lot of truck traffic, a lot of commerce between both cities, a lot of truck traffic going through I-10. So there was a huge mix of trucks along that corridor, especially from West Texas. And so why this problem? In 2000, if you guys remember the recession in 2008, the economy was slumping. That's when I noticed there was less trucks out in the freeways, more motorcycles. Gas prices were up. People were changing modes. So as the economy started to recover, this is something that we noticed in El Paso, there was an increase in truck traffic, especially those that we consider heavy vehicles. Now, as they say, as the economy recovers, so does the increase in truck traffic. So you'll see more of that if you're driving here, actually driving up to Portland, just as I left Corvallis, I was stuck between two semi-trailers on each side. It's kind of scary because I guess the pavement just shakes your car. You're like, ah. So the increase in truck traffic poses an increased hazard to passenger vehicle traffic. And so have you guys ever been stuck behind a truck and you're trying to get maneuver and there's another truck in front of you? It's just kind of hard to see. It poses problems for many passengers. It also poses problems for other truck drivers. So as that increases, you're going to see some more hazards. In a study by the Federal Highway in 2010 and also NHTSA, the National Highway Transportation Safety Administration, in 2009, mentioned that large trucks were more responsible for more fatalities than passenger vehicles. Right? Larger trucks, large mass, crash into a small little car, like you saw on the previous slide, you have nothing left other than just some wheels underneath a big truck. So there's a huge effect with regard to large truck crash involvements. So some basic statistics behind this. So my student and I were looking at some national statistics with regard to large trucks and doing a literature review with regard to this area. And we kind of found that about 4% of registered vehicles were trucks, 8% of VMT in 2008 were truck-related vehicles, and about 11% of motor vehicles involved crash deaths in 2008 were with regard to large trucks. So those are pretty large numbers. So we kind of, through our literature review, we also kind of discovered that, what were some of the costs associated to these large truck-involved accidents. So when there's, on average, costs per fatal crash when a truck's involved, you're seeing almost $3.6 million with regard to a cost. This is from some of our literature review that we were conducting. On average, cost per non-fatal crash was about $200,000. And on average, for property damage only or non-injury, you're looking at about $15,000. So there's huge amounts of money entailing with, when you're dealing with large truck accidents. So when there's a truck involved or large vehicles involved in accidents, there's always going to be some type of societal effect, or any crash, that is. But when you're looking at large truck accidents, as you see in this picture, they tend to take larger spaces on the road. They slow traffic up. When they get into accidents, you see more damage. You see lost goods spilled over the road. And so there's a remarkably high cost associated with these types of accidents. From a societal standpoint, you have expenses related to loss of life if there's fatalities involved. Medical attention for those extreme injuries after such accidents, short-term and long-term physical and emotional effects. Then you have the economic impacts, especially if you have trucks carrying goods. In Texas, we saw a lot of trucks turning over. Between April and May, you have these high winds coming in. You have these sandstorms. And some of these truck drivers, and because our speed limits in Texas are pretty high, 75 miles an hour, even though some of these truck drivers are supposed to drive 55, 65 miles an hour, they're still speeding down these roads to get from point A to point B. So we were seeing some of these trucks tipping over and seeing some of these accidents. So a lot of goods were being spilled over. So there's a high cost with regard to these trucks. So this was kind of motivating the research. So the more we digged into the literature, the more interested we were looking from an exploratory standpoint. Why are these accidents, these crashes occurring? Is there, what studies have been done to kind of talk about some of those issues? So, just from a motivational standpoint, in discussing with some of our Department of DOTs and TxDOT, and talking to some of the MPOs, El Paso has a very active MPO, and just from our discussions with them, they were kind of just interested. Hey, so why are these accidents happening? Could we do anything about it? Is there something that we could do to, maybe help the trucking industry, maybe regulate more the way drivers are trained? So what is it that we can do to facilitate or improve this? And so in the state of Texas, just from an economic standpoint, in 2008, they estimated about $22.9 billion worth of losses with regard to crashes in general. This is the state of Texas, just very large. From 2006 and 2010, in the U.S., the total amount was about $107.4 billion. So this is Texas just 1 year. I didn't add all the other years for Texas. There's a lot of accidents occurring in Texas. There's a lot of large trucks going through the state of Texas, just from the commerce between Mexico and the U.S. and anything going through from the west to the east coast. So recent data in 2010 indicated that around 3,000 deaths occurred in 2010. This is from crashes. Around 59,000 serious injury crashes occurred, and around 82,000 people sustained serious injuries in these accidents. It's a large amount of accidents. Once again, size. You have urban areas separated by very long rural stretches of road. Is it speed? What is it? What's going on here? So we were digging deeper into the literature to see if anybody had addressed some of these issues, and there was hardly no papers at all, no research out there to really indicate, why are these crashes occurring, and what about the injuries sustained in these accidents. So very few studies have investigated injury severities associated with large truck-involved crashes, especially utilizing specific state data. Now, we were kind of lucky that in Texas we have a very good crash data reporting information system, which I will present in a few slides. So there was a substantially large data set that we can dig into and investigate to come up with some of these, the reasons why we have these injury severities. So research objective. So we finally motivated the problem. Okay, this is what we're going to do. We're going to look at the injury severities with regard to large truck-involved crashes, incidents, accidents. So from an purely exploratory sense, research objective number 1 was to analyze injury severities, as I mentioned earlier. Our second objective was to, because we have this large data set, Texas is very big, spatially, and we have a huge diverse population, right? You have different cities separated. Each one is very different. Individuals behave differently in the state of Texas. It's not very homogeneous. So part of this study was to, although we have this crash data, we don't have all the information with regard to that. These were police reports given to the state to come up with, to kind of look at the types of accidents. So there was possibly some information that was missing, which we, to account for that, we call it, we say it's unobserved heterogeneity. There's factors that may be influencing some of these accidents, maybe the behavior of the individual, even the police reporting on the accident may have not been, it might have been not a good day for him and so forth. So there's a lot of unknown factors with regard to filling out this data. So how do you account for any of that? So there's these factors. So the first one is to come up with injury severity models. And second was to account for any unobserved factors that may be influencing some of these injury severities or the reporting of injury severities. So why is this important? So it's very important to always have some type of thorough understanding of why an accident has occurred, or maybe to say why would an accident occur in a specific location. And then this will provide, in knowing this information, this will allow us to come up with more effective countermeasures, or to develop more effective countermeasures to mitigate or to reduce the injury severities that may be sustained with regard to these types of crashes. So from a research standpoint, our region or the area of interest was the state of Texas. So we had a crash database that had every crash that occurred in the state of Texas for multiple years, which I'll mention now. So we looked at all the cities, El Paso, Odessa, Midland, all the cities that had some type of reporting system that then went into the CRIS system, the database. So we had a very large data set, which I'll mention how large in a minute. So everybody knows where Texas is at, right? Just to make sure. All right. It is a state. They're kind of southwest. Well, they do. You guys have heard the thing? Everything's bigger in Texas. Trust me, it is. The burritos. When I ordered burritos, I was used to the Taco Bell little bean burritos. You ask for a bean burrito there, it's just bigger than Chipotle burritos. It's pretty big. For $1.25. On Fridays. To get people to the restaurant. So yeah, everything's bigger in Texas. No vegetables, lots of meat. There we go. So from a research standpoint, so we have the motivation, we know what we want to do, we have some data, we know what we want to do. So research steps. So once we collected this data, I'm just kind of follow you through what we did and then kind of present the rest. So we have this large data set, and through our literature review, we defined some variables that others have found to be significant with regards to crashes and injury severity. So we said, okay, well, we have a beginning, a start to our research. We'll look for these columns of information in this large database, then we'll isolate to use for future modeling. We then, because these data spaces are so large, big data, we needed to come up with a process to look at the data, clean the data, and come up with a usable data set for the research. So as soon as we did all that, we went back into the literature to see what have others done, what have others worked on, or what models have been proposed to look at injury severity modeling, and how did they estimate these models. And then once we've identified a modeling approach and an estimation approach, how do we infer on the variables that were significant? What is the meaning of this? And how could we use these or the information gained from this process for future policy making or safety decisions that need to be made by safety professionals? So it was a pretty long stage of steps. So the database. We use the Texas Crash Database, which is called the Crash Record Information System, CRIS database. It's all the police reports for a year. They're collected in some PDF format or some paper format, sent to a third party. They go through it and they give and provide a huge spreadsheets of accidents. Now, of all the different accidents that occurred in the state for a particular year. Now, for each year, you received numerous, like around 5 to 6 Excel sheets. Each one had about almost 500,000 entries, almost 500,000 entries. So the state is large, a lot of accidents. So trying to work with these different data sets and to try to merge them into a usable data set was very hard. But the one thing that we first verified or looked into the data was, okay, do we have at least a column that discusses the injury severity sustained in with regard to a crash? Once we identified that there was such a column, then we came up with developing a way to process the rest of the information to come up with a usable data set that had this column in charge. So we, since we had this huge amount of data, we were able to look at 5 different injury categories. Most of the research out there through our literature review typically clumps some of these into 3 groups. No injury, some possible injury, and then fatalities. So they kind of group those. So just for the sheer mass and how large this data set was, we were able to actually separate these in different columns. And I'll show a statistic on how we did that in the data with regard to each of these steps. So in our research, we considered 5 injury severity levels that were contained in this data set. We looked at fatalities, incapacitated injuries, non-incapacitated injuries, possible injuries, and non-injuries, or property damage only. We followed the Kabakal scale, which is a fairly well-known scale with regard to severity reporting, injury severity reporting. So typically, you'll see more property damage only related to crashes compared to the number of fatalities in an actual data set. So the further down you go to the scale, the more information you have or more crashes regarding that are found in your data sets. So we had these databases, and it took my student and I several months to come up to a way to kind of merge these different data sets. We had 3 databases that we wanted to merge for each year. The first one was the vehicle-related characteristics of a crash, and each of these had a crash ID that linked them all together. So we had 3 separate databases for 1 year, and we tried to link them by the crash ID, which we did. So we had information related to the vehicle itself, information regarding to the person, such as age, gender, and other socioeconomic characteristics that were provided in the reports, and also injuries sustained by the individual and so forth, and information with regard to the crash itself, location, geometry, and so forth. So there was a lot of information in this data set. So what we did was we went through this data and we sifted through it, and we followed this process. We decided to work with, at the time, the most recent set of data was from 2006 to 2010. Each database was more than 500,000 observations. So it was for any of the computers that we had in our lab, it took hours just to kind of get something working in Excel. So we ended up purchasing a server to kind of help us with the data analysis. And we switched from Excel to SAS. We just put everything into SAS, make our life a little easier. So we looked at sifting through the data. We looked at interstate highways, and so all crashes on interstate highways first. Then we sifted through the data and looked at just large trucks on interstate highways, and then we looked at vehicle ID, person IDs, and crash IDs, and merged those together, along with the maximum severity of that data. In the end, we came up with a usable sample for this research. So over this 5-year period, I'll mention in the empirical settings, but I'll mention now we had over 20,000 observations for 5 years. And I'll discuss this split. So once we had a usable data set, it was now to Okay, what do we do with this data? What is it that we want to do? Well, we want to analyze injury severities. What models exist out there to allow us to come up with some injury severity models? So the first question we asked ourselves, well, how detailed is our data? Very detailed. We had over 100 plus columns of information, just information with regard to the crash itself. So it's very extensive. Other states may have 20, 30 columns of related information. We had over 100 columns of information with regard to these crashes. So there was so much data. So, we know that we had a pretty detailed data set. However, we know that Texas is extremely large and very diverse. And knowing that there's bound to be some unobserved heterogeneity that might be likely, that it might exist within this data set that we have to account for. Why do we want to account for some of this? Because you have individuals may behave differently when they're driving. There's a lot of differences between risk-taking behaviors, physiological factors, driver training, our proximity to the border. We did have traffic coming in from Mexico, completely different driving standards, or even testing as far as getting your licenses. So even interpreting the signs and road signage and stuff like that. So that could be a factor in our data sets. So in the end, after going through all the different modeling approaches, we said, okay, well, let's look at the Mixed Logit model. So I'm going to present a little bit about the Mixed Logit. If you want to know more about the Mixed Logit, feel free to take a class with econometric modeling in it. I do teach it at OSU, but I'm sure that they teach it here at PSU, or somebody teaches a class similar to that. So I'll just briefly touch on the Mixed Logit, and then I'll give you guys a quick reference. So the Mixed Logit is also termed the random parameters model. And why is it a random parameters? What does this model do? What does it allow us to do? So if we look at previous modeling methods, they've used ordered models, ordered probability models to look at injury severity, to categorize these injury severities. They've used nested logit models. They used multinomial logit models. So I want to just briefly touch on a multinomial logit model. I don't know if you guys have heard of this before, but Wikipedia. You can do a quick search on these models, but just to kind of give you an idea, the standard multinomial logit model allows you to estimate a model for injury severities in this case, but in the end, it assumes that the coefficients that you're estimating are fixed across the observations. They're completely fixed. They're the same for everybody in that observation. That might not be the case. Like I said, there's maybe unobserved factors or outside factors that may be influencing some of the, maybe influencing the model or those coefficient estimates from the outside or even from within the models. So you have to account for some of that. So if we assumed the multinomial logit model, violations of this assumption can occur if there is some compelling reason to believe that the parameter vary across observations. In our case, we knew that these parameters weren't fixed. We could not use the multinomial logit model. And we had a suspicion that some of these parameters would be changing across. There's some of them may require some additional method to account for that. If we don't account for this unobserved heterogeneity in our models, this may result in the potential bias in inferring upon what's been given to you by the model. So you may have erroneous statistical inferences from the modeling approach. So we wanted to take into account all that. And so this is kind of if you've never seen these logit models, bear with me. This is simple math. Everybody has taken algebra, right? I made it as simple as possible. So just to kind of give you a general idea how the mixed logit model looks like, we'll start off with a simple linear function. There you go, linear function, where SIN is the severity function determining the injury severity category. In our case, we have 5 categories, from fatality to property damage only. So we're going to, the idea was to create 5 separate linear equations for each of those categories, and then fill those in with contributing factors on why those may, if we can help explain the crash outcomes or those injury outcomes. X is the vector of explanatory variables. So if you think of the Excel spreadsheet that I was talking about, it's all those attributes, all those columns of information That helps, some of that information may help us explain a specific injury severity. Then the betas in this equation represent the estimatable parameters. So just to go back to your algebra back when you were in 3rd grade, or 4th grade, you guys are pretty smart. Remember the equation y is equal to mx plus b? Very similar. Okay, y is equal to mx plus b. M is the slope, right? X is whatever information you have. In this case, it could be a number or whatever. And b is some, y-intercept, right? Some constant. Well, we have similar effect. Well, here epsilon is not our constant. This is the error term in the information. But when you do the modeling, you tend to use, we include a constant if it's significant into the model. So kind of give a little flavor to what this is. So we start off first by defining these equations. And then to kind of define more this mixed logit model, we assume that if the epsilons, these error terms, if we assume these to be generalized extreme value distributed, we then can use this closed form equation to allow us to come up with the probabilities of a large truck involved incident and having severity outcome I. I is our choices, right? Fatality, incapacitated, non-incapacitated, possible injury, and property damage only. So now we can come up with those probabilities of a specific event occurring, or of event happening, in this case, a large truck involved incident. So this is kind of borrowed off a famous author named McFadden. And so there's some resources on him if you want to look him up. If you can always come and ask me questions with regard to him afterwards as well. So, but we extend this notion. So this is kind of still like a multinomial logit per se. What makes this a mixing or mixed logit model is that we now define a density function, right? F beta given phi. This is simply a density function of beta with phi referring to a vector of parameters of the density function, mean and variance. So what does this help us do? With this, then beta can now account for segment-specific variations of the effect of X on large truck-involved crashes. Well, so why is this important? Well, now, instead of in the multinomial logit model, the betas, when we estimate that model, betas are fixed. We say, here we go. The estimation procedure gives you some number, and that's it. Here, with this procedure now, we can say, hey, beta, and you're not a fixed beta anymore for this attribute. Let's say for the male variable, your coefficient can vary across some distribution now. Instead of assuming a fixed parameter, we can say, hey, your beta for male can now vary across some distribution. It could be a normal distribution, a log normal distribution. You get to choose. The term mixing comes from that. You can mix the distributions in these models. Mixing. So we're using a distribution to allow us to account for some of these unobserved variations, or these variations in the data set. So what does the mixed logit do? So for those who haven't taken econometric modeling or have taken some of these advanced courses, in the standard multinomial logit model, there's an assumption that we term the independence of irrelevant alternatives. It's a whole class in itself, but just to briefly discuss it, it's a problem with those models. With the mixed logit, we don't have to worry about that. This problem is taken care of because we have a more general arrow term structure. And with the mixed logit, we can now test the betas if they're a random parameter or a fixed parameter. So in our modeling procedure, we can say, here's my equation. Here's my factors that I'm considering in my equation. Male. This is their age. This is the type of vehicle, whatever they're driving. And their betas, we can assume to be fixed, and some we can say, hey, I'm going to let the beta for the male, the coefficient that we're estimating, be a random variable itself. And we're going to use a normal distribution or a log normal distribution to see if it's a significant assumption, if it's an assumption that we can make that parameter may vary across those observations. And once we get to the results, the easy stuff, to kind of describe, it'll make more sense. So this is just kind of a little theory portion of the class, of this seminar. So to estimate these types of models, we use what's called simulation-based maximum likelihood estimation. Now, you don't have to worry about programming any of this. There's already off-the-shelf programs that do this for you, it's pretty easy to do. You simply get data, put it into this program, define the y goes to mx plus b equations, those simple linear functions, and tell the program which of the betas you want to study for if it's a random parameter or not. And at the end, you get an output with some statistics. So it's, although this theory is like, oh, I'm bored, you're making me go to sleep, Dr. Hernandez. In the end, the application's pretty easy. You're like, oh, wow, anybody can do this, right? Then you can put it on your resume, know how to do a mixed logit model. People will be like, wow, mixed logit, what is that? It's a mixed logit. Moving on with the presentation. So if you want more information on the mixed logit model, one of my professors, Fred Mannering, who's the third author, so Dr. Washington, Carla Fatis, and Fred Mannering, Dr. Mannering, have published a book, second edition, that talks about more on the mixed logit model. Relatively easy. They have data, they show the data applications, the model, and how the inferences as far as the information, the variables that were significant, and they touch the theory in a pretty easy way to understand. It's a very good written book. I use it a lot for some of my classes. It's called Statistical and Econometric Methods for Transportation Data Analysis. So if you're interested, that is the book. So the fun stuff, the empirical setting. So now that we have the data, we identified the modeling approach finally. Yes, and then we identified a program, a software that can do it. In this case, we used what's NLogit. I didn't have a slide for it, but NLogit is the software that's produced by a professor by the name of William Green. He's helped develop the software over the years, and now it has some of these more sophisticated econometric modeling techniques embedded in the software. Relatively easy to use, and it allows you to, you can do from regression analysis, which some of you have done before, I imagine, to even using calculator. 5 times 5 is 25. There we go. So you can do all these things in that program. Very simple, and even allows you to build some of these more sophisticated models, and it's relatively user-friendly. So we identified all these factors. Now let's do the experiments. Let's see what we get from our injury severity analysis. So our idea was, okay, we want to seek to model the maximum injury level sustained by drivers involved in a large truck-involved accidents. Okay, so we have, what is the maximum injury severity they sustained? So we had 5 categories that I had presented before. Those were property damage only, possible injury, non-incapacitated injury, incapacitated injury, and fatalities. And remember, I said, so once we went through this data cleaning, data processing. In the end, we came up with about 20,000 observations, 20,500 observations for between 2006 and 2010 that met our criteria. Interstate large truck accidents that had a lot of information. And we had the injury severities with regard to those crashes. So we had this information. Almost 89% of them were property damage only, and about almost 0.4% of them were fatalities, 78. But you see a pretty, this is fairly typical for accidents. But the number that stuck out to us was 78 deaths over a 5-year period with regard to large trucks. In addition to these incapacitated accidents, 463 of them. Those are pretty severe accidents. So that's still, if we want to go 0 accidents in the next few years, it's still pretty bad. Very substantial, a lot of costs with regard to that, especially for the state of Texas. So I apologize for I was told about text size, but this is just to kind of show you some descriptive statistics. So and this is not all of the data that we went through. Okay, these are just some of the variables that we felt through our literature review may be significant in our model. All right. So we looked at, for example, for all these variables, we had a mean. Most of them are less than 1 because we created dummy variables. This is 1 or 2 variables. For example, just to highlight right here, let me see if I can get the mouse to work. Here we go. Number of lanes on highways, 1 if 4 lanes in one direction, 0 otherwise. Okay, so we created these dummy variables for specific situations. Like I said, we had numerous columns of information, and we had to, it took literally more than 3 months for our students in the lab to kind of pinpoint, okay, these are the variables that we're going to look into. So it's a very large data set, and we're still working with some of that. So this is just to kind of show you what we did. We identified some variables in the data set. We created dummy variables from that to see what would be if those are influencing some of these injury severities. Oops. Thank you. Sorry about that. I apologize. I was about to have a heart attack. All right, here we go. So model specification. 5 equations, 1 for each of the injury severity levels. So modeling is an art, not a science, right? Everybody's different. So Picasso, can anybody draw like Picasso or paint like Picasso? No. He developed that over years. Every artist is different. Every modeler in this area is different. So what do I mean by that? There's so many variables. You just can't, by process of elimination, it'll take you years and years to put all the variables and find them all, the ones that you think are going to be significant. It takes time and experience. So when I told my students in my lab, hey, you guys, be patient. All right? Just go through the variables. First, let's go through the ones that have been found to be significant in the field. Put those in first into the model, and then look for ones that would be specific to the state of Texas. And then other things. So it takes time. It's a learning process. So what we did first was we looked at the human aspect, right? Humans err, right? We're not perfect drivers. So there's different situations, different things that we have to consider. The age of the individual, their time, how long have they owned their license, where were they licensed, how long have they been a truck driver. So this information was in those databases. So they had to go through that information. So we start off with the human aspect first in our models. And then once we identified some of the human aspect variables or variables related to the individual, we moved on to the vehicle, in this case, large trucks, some characteristics with regard to the large trucks. After we identified those variables and we found some to be significant and they were interacting with the ones with the human, so we're like, okay, good, this is good. Now we're growing, we're developing a model. We looked at the roadway, right? Yeah, this is in terms of spaghetti bowls. Have you seen those? El Paso has a spaghetti bowl that takes you to Mexico. It's pretty bad. You guys never driven anything like that before? Oh, I forgot you guys we're in the northwest. Nice and clean, straight, beautiful. Go to big cities that have havoc. Yeah, it's pretty bad. Imagine driving that, right, during off-peak. Now, once we identified some roadway characteristics, geometries that may be significant in this model, we looked at the environmental models, the environmental variables, weather conditions, time of day, month of the year, day of the year, so forth. Before I put the next picture up, did anybody go Black Friday shopping? Did anybody go to Target? Was anybody a target of Target? That was me. So I'm happy that Target was. So environmental issues, don't be Target, or else this is a Target truck inside a huge pond of, I don't know how it landed there, but. So we look at the environment. Maybe you thought it was an ice road trucker. Sure didn't sustain it. But we looked at all these different variables, okay? So not to bore you, I didn't want to put all the tables out there. I summarized everything. So once we went through this process, we methodically went through each process instead of just going crazy and, no, what variable works? We went systematically, looked at the variables that were significant, and boom, we came up with some findings for our model. After a year and a half of modeling and data processing and identifying the correct modeling approach, we came up with something that looked relatively good. So just to kind of describe these different tables. So from a driver characteristics point, this human aspect, we had several variables that were significant. One was male, and these acronyms within these brackets are the injury severity category where they were found to be significant. Red means increases the likelihood of that injury severity. Green decreases the likelihood of that injury severity. So male decreased the likelihood of possible injury. Any idea why? Think outside the box. Truck driver, yeah, it's just. No, that's good.
Oh, I don't know.
Any answer is a good answer. So they might not have reported their injury. Is it the machismo? It didn't hurt. You go home, you're like, oh, my back hurts, right? So, okay, that could be one.
Most of the truck drivers are male.
Most truck drivers are male. Okay. There was females in this, by the way. All right. That's good. Any other reasons? So through our literature review, we found that, and other studies found that our physiological ability, we can sustain greater injury impacts. Well, and then once again, it could be because we don't want to report the true. It didn't hurt me. I'm a man. I didn't get injured in the accident. So there could be. We don't know. There's these unobserved things that we don't know why individuals may have underreported their injury. So these are questions. To us, it was baffling. Okay, male. At first we thought, yeah, because he's a man, he's strong. But there might be some other things that might be involved. So hold that thought. Remember this random parameters notion? So male, okay? And then we have different age groups. So 25 to 35, if you're between 25 and 35, that decreased the likelihood of possible injury. Once again, maybe you're strong at that age. I don't know. I'm not 30. I'm older than 35, so I'm kind of weak. 45 to 55 years old increased the likelihood of property damage only. I don't want to guess why. Maybe because we're older, right? You just can't drive. I don't know. So there's a lot of possibilities there. So that's from the human aspect. So temporal characteristics, we look at time of day. Between 3 to 7 p.m., you have incapacitated and possible injury decreased. Those likelihood. So why between 3 to 7 p.m. do you think it decreased the likelihood of incapacitated injuries and possible injuries between that time period? Any idea? Yes.
Because there's less congestion, he was going slower.
Perfect. Yeah, that could be a reason, right? That could be a reason. That was a reason that was found most common in most of our literature to be a reason. Okay, good.
Or less speed differential.
Oh yeah, exactly, especially during those periods of times. Okay. What about between 12 and 6 a.m.? That increased the likelihood of non-incapacitated injuries.
People tend to drive faster
At night, okay. Drowsiness could be an effect. We don't know. There's other things that could happen, right? So there's a lot of so we did have a drowsy factor. There was other variables. We didn't find those to be significant, but we felt that hey, there's some possibility that might be drowsiness. You have these off-peak delivery times, especially from in Texas. You have people driving through to go to the East Coast along these long stretches of rural roads, right? So yeah, those are possibilities. September through December decrease the likelihood of non-incapacitated injuries. So what happens between September and December? There's more. You have the holidays, more traffic in the roads, filling up the also weather can be an issue. People tend to slow down a little bit, right? So there's different ways to explaining those variables. So we kind of went off what the literature had discussed, and we kind of adapted that to Texas itself as well. We see a lot of rain in Texas, especially in the east side of Texas. You have land use characteristics, rural versus urban. Rural roads increased the likelihood of fatality and non-incapacitated. Does that make sense? Is it pretty straightforward? Rural roads, right? Tend to drive faster, possibly. You're alone. Some animal darts in front of you. You try to, stop. So there's factors there. It makes sense. The sign of that variable made sense to us. Similar to that of urban, right? You have the varying speeds within the time of day and so forth, so that made sense. Traffic conditions, of course, we looked at ADT. Weather characteristics, clear weather, increased fatalities and property damage. So clear weather variable, when it was clear, it increased fatalities and property damage. So Why would clear weather? Sometimes we feel more comfortable, right? It's not raining, it's not snowing, we tend to speed a little bit. It could be some of that psychological. So there's some of the literature we found behind that was we feel safer. Well, who has a nice car here? I have a Toyota Matrix. Meaning everybody has airbags and these, we tend to compensate for the safety features that we have in our cars, and it's a beautiful clear day, we roll the windows down, we put our glasses, we lean back in our car and drive 100 miles an hour down the road, right? It's a beautiful day. So I don't know. So we're kind of going off the literature there. Road geometry, 4-lane, right shoulder. These are some of the variables that came out to be significant. So this was our model. So what about this random parameter notion? So which of these coefficients were actually considered to be random? And what is the significance of that? So if we estimated a regular multinomial logit model or any of these other order probit models and so forth, and the parameters are fixed, then we can say that for surety, male decreased the likelihood. That means the sign of the beta was negative, right? It was a negative number. The coefficient was negative. And we can say, in these other models that this is a fixed parameter, and this is true for all the observed data that we had here. We can infer that this holds true for the set of observations. But for the random parameters, you said, okay, now that we have this model, let's test the betas. Let's see if there's any variation in observation with regard to this variable. So we did find several variables to be random, and we found these coefficients. Although the sign is negative, let's say for the male indicator, the parameter was found to be normally distributed with a mean of negative 3.936 and a standard deviation of 1.62. We got that information, we went to our normal table, and we got these probabilities, these percentages. What does this suggest? What does this information tell us? Well, it suggests that about 0.7% of large truck-involved crashes involving male drivers, on average, were more likely to result in possible injuries. So we switched the sign. Instead of it being less likely, for about 0.07% of those drivers, the sign changes. It does matter. They do receive some type of injury. There's some type of possible injury that they sustain. So this came out to be significant in the model. That for 0.07%, we just say of this observed information that we had, the sign changes from negative to positive in that coefficient in that equation. What does that mean? There we go. So another variable that we found to be random was the age group indicated between 45 to 55 years of age. And we found it to be significant in the property damage only equation. Another one was for the possible injury, a utility function. We call it utility functions. This parameter was normally distributed with 1.097, a mean of 1.097, and a standard deviation of 1.86. We went back to a normal table. We came up with some percentages. This implies that about 72.2% of large truck-involved crashes with this age group, on average, were less likely to result in non-injury crashes. If we would have assumed a fixed parameter model, we would be inferring incorrectly. That, everybody here does, within this data set that we analyzed, is assumed to have this effect. Now, so the age affects property damage only in a positive way. But in reality, by letting that parameter vary, we see that for a big portion of it, the sign really is negative for some of those individuals. So that age group are less likely to get in these types of accidents or to have property damage only. So there's variations in those parameters. So we capture that through this model. It at least gives us some idea that, hey, there's some unobserved information or factors that are influencing these variables. We're trying to at least capture some of that. And then we try to infer why is that the reason? Why is this the case? So it allows us to kind of account for that. Now, we found 3 of the constants to also be random parameters with means and standard deviations, and those could just be, most likely deal with those types of injury severities, information that we don't have or under-reporting by police officers with regard to those injury severities. So I just wanted to show these two, age and male. Those were found to be significant in the random parameters model. So, okay, we developed this random parameters model. Is it the correct model? Are we really, are we using the correct model for us to infer upon? So what we did is we could develop the hypothesis test. And this is pretty standard. We looked at, okay, well, the null hypothesis that both the fixed parameter model, which is just simply a multinomial logit model where the parameters are fixed across the observations, they're not allowed to vary, is equivalent to the random parameters model, where some of the parameters do vary. The alternative is the reverse, that the random parameter is superior than the fixed parameter model. So what we did was we conducted a log likelihood ratio test where we had 6 degrees of freedom, and once we conducted this, we compared the log likelihood. The log likelihood is a piece of statistical information that's provided to you when you estimate these models. We used that information, and we compared them, and we did a log likelihood ratio test. And the ratio test came out to be that the chi-square, which is the value was 62.94. We went to a chi-square table. We had the degrees of freedom. We had our information. We went on there, and we found that it was that we should reject the null and accept the alternative. That the random parameters model was a more superior model, or that we reject that they're equivalent, both the fixed parameters and random parameters. So this kind of showed us that, hey, this is significant. Out in the literature, though, not very many people perform this test. The reason is if you find one random parameters, then the model is a random parameters model. But we wanted to go a little further and show that, hey, this is the case. We know this should be a random parameters model, and this is why we use this. So just some key findings with regard to this study. That just to briefly cover it. Higher traffic flow reduces the likelihood of fatalities. Right? We found that to be in the model. Pretty obvious. But increases that of property damage crashes, right? Fender benders, right? Bumper to bumper. I'm pretty sure everybody here has gotten a fender bender, right? Or at least crashed your bike into something, right? No? Okay. Or skateboards. I like the skateboard. Crashes occurring in rural settings result in higher likelihood of fatalities and non-incapacitated injuries. In contrast, crashes occurring in urban settings result in lower likelihood of incapacitated and property damage only crashes. Time of day, such as between 3 to 7, results in a lower likelihood of fatalities. Compared to 12 a.m. to 6 a.m., resulted in a higher likelihood of non-incapacitated injuries. Summer is likely to increase likelihood of incapacitated injuries. So this is some of the information that we found through our modeling process. So future work. We've just finished the rural versus urban. That was a variable that was significant in one of the models. And we just finished that model with my previous PhD student, and we found that there is a significant difference between both. By splitting up the data in between rural versus urban, that the models are significantly different, and that we should consider that split, with regard to urban settings. So if you think of Texas, you have those very few large cities, El Paso, Dallas, Austin, Houston. So you have these, big cities, and you have those smaller little cities around. And so they're very different. So we were, the data told us, hey, and also the modeling said, yeah, you should separate these models apart. We're also in the works of finishing the time of day. Time of day was important. We wanted to know if that had, if we can separate the models further with regard to time of day, to see if there's any new information that we can gain from the data set that wasn't significant before in other models. So you can kind of consider this model as, let's look at all the data out there, let's develop a model. And then from there, now we're kind of looking at specific models, urban versus rural, time of day, transferability. Thank you very much, Dr. Mansur, for the data. I was kind of looking into that, what variables are the same with regard to traffic. So why is transferability, why could that be a good case? Well, truck drivers cross states every day, right? So they're, as compared to us, we drive around the same region, maybe the cities, and we very rarely do we have to cross different borders, state borders. If you look at a truck driver, long-haul truck drivers, they cross multiple states, right? So there's one notion that some of these truck drivers could be the same across different areas. So they might have suffered accidents somewhere else. So we wanted to see if some of our truck models, these severity models, can be transferable to other regions. And so look at that aspect. And to finish, right on time, you can read the paper. It's in print in TR. Got accepted a while back. They said that they were going to mail it out to me soon. So you guys can read. You can probably Google it and find it now. Family guide picture target. These are the sources. So if you're interested in that, you guys can go ahead. You always source everything. You can never claim anything is yours. Always put the source. With that said, any questions? I know this is like a mini econometric class.
So for like the fatalities, did you know any common like factors that all of them have the same factor?
Well, not all. Yeah, we tried that. We first, our students, because modeling is an art, not a science. We tried putting. The thing is, when you're looking at these types of models, you don't want to put the same variable in every equation. Maybe there's 5 equations. You can put the same thing in 4 of them, and you have one to compare off of. It's just the way the technique is. So I encourage you to take an econometric class from one of your professors. I'm sure you'll see some of the methodologies behind that. But some variables could be in every equation. For example, distances or types of interstates. But when you're looking at these dummy variables like male, gender, they may not be significant in every injury category. But yeah, we started off with that just to kind of see, which ones are significant. And you start. It's part of the modeling aspect. You want to eliminate things. Yes.
So you said like state of Texas has kind of, mine was up in Mishra. You said the state of Texas has like more truck crashes than any other states, right?
Well, yeah. Well, there's more truck traffic that goes to the state of Texas that has the possibility.
So I was driving through Texas 3 weeks ago in winter break, and I realized that you can only drive. I was driving through like smaller cities, so you can only drive in right lane, and left lane is especially using for if you want to pass. So I mean, obviously the speed zone is really high, 75 or 80. Yeah. So the only problem I had, like I was going really fast, and I can only drive in right lane, and there's like huge lines of trucks ahead of me. So I feel like, don't you think like the state policy of using just one lane, and you're driving super fast, and you don't have like a good line of sight since you're driving right behind the trucks, and if you get like in a super curvy turn, and if you have like a sudden grade change, I mean that would increase the chances of getting crashes.
Oh yeah. Certainly when you're driving 85 miles an hour, right? And so, that's a very good question as far as where should trucks be, in the traffic flow. It's a political thing. I remember when I was in Indiana getting my PhD, they were looking at a separate roadway just for the trucks because, the Borman Expressway, I-90, I-80 and I-94 up in the northern part of Indiana to Chicago, there's so much truck traffic. And even going through I-65, they're looking, there's so much truck traffic. Why can't we just get a separate lane just for trucks? Give us our space. It's really a political issue. I mean, all we can do is, hey, you know what? This is the data. This is what we're seeing. You might want to use this in your decision processes. That's why we do some of this work, is to see what implications come out of this work and what we can recommend, to the safety professionals, the engineers. Yes.
So when you came up with, kind of the larger factors, did you look at a lot more than the ones you did, and the ones that you showed us were just kind of the most significant findings, or how did you pick which factors you were going to kind of examine?
Good question. So we first started off with our literature review. We found out what others have found in different types of accidents when they're dealing with injury severities. So if we go back to my, there we go. So what we did is we went through the literature review. And by the way, there's this thing called Mendeley. Have you guys heard of that program? It's for literature. You can store literature and it's really nice if you want to do a quick search and put all your papers in there. So when you start referencing this, it makes life easier. So it's better than EndNote, whatever. So that was my plug. What we did is we went through the literature and we said, okay, well, these are the variables that were found by other studies to be significant. Do we have those in our data set? If yes, let's do those first. Let's try those out in our data set. And then, so once we went to what the literature had found, from a research standpoint, we said, okay, well, now let's start looking at things that may be specific to Texas, right? You have the percentage of international drivers in the state. So we looked at if they were licensed in the U.S. or not. We looked at variables like that. So we were putting in that information. We looked at licensing by state. There was a lot of truck accident crashes in the state of Texas from licensed drivers from other states. So we looked at, well, is California truck drivers better than a Texas truck driver? Is a Oregon truck driver better than a Reno Nevada truck driver? I don't know. So we have all these different licenses, and so we tried so many different combinations. So we started off with what the literature had, then we went what is state-specific variables, and then we kind of got to think outside the box. That's the art part. Could this variable be significant? Why? Maybe personal experience to you. How far, proximity, accident proximity to intersections or crosswalk, whatever it is. So you start off with personal experience, things that you see. Think outside the box. So a lot of our students would do is they go to Google and they start looking at images of truck crashes, and they think, oh, wow, that's a good variable. Let's see, do we have that information in our column? And they start devising variables from that. So we first systematically looked at the literature, then we moved on to state-related specific variables, and then we kind of started thinking outside the box. Good question. Yes?
Were any of the human aspect variables that you were talking about, did any of them show any substance abuse, like DUI?
Yes. So
I'm just curious why that wasn't, was it significant or was it not?
They weren't significant. There was even ones for if they were under the influence of alcohol or any other foreign substance. They don't say marijuana or any of that. It's just some of the information that is not there, but there's variables that we created now. Those didn't come out to be significant. We're dealing here with truck drivers. Now, truck drivers tend to be more regulated, and so we kind of figure that might not be significant. However, that could change now that we have 2 states that are legal. I don't know. I don't know. I really don't know. But those variables could become significant when you look at the passenger demographics. That's a good question.
Over time. So before we thank Dr. Hernandez for his great talk today, next week's talk is
Garling from PD from Cont'd, urban footprint.
Yeah. Okay. So with that, let's give Dr. Hernandez a round of applause.
Feel free to contact me anytime. You can look me up on the web. Wait, Sal Hernandez, you might find like 1,000 of us. So put Sal Hernandez Corvallis, you'll find one. So, all right, thank you.